So in chapter 10, we're looking at series and sequences and sigma notation. And we're going to look at some different types of sequences, and then we're going to look at how to use sigma notation to represent sums. So a sequence is just a list of numbers, and then the items in that list are called the terms. So these guys are the terms, and then this is their place in the list, so the position. And we can have finite sequences that have a set number of numbers, or we can have infinite sequences that have an infinite number of terms in them. And generally what we're trying to do with these is we want to write a rule or a formula that can predict how to find the term. So let's say I want to find the 51st term in this sequence. Well, I don't want to have to keep adding 3 a whole bunch of times. So my aim would be to find an explicit formula where I could find what that would be based on n, which is the position number, right? So if I want the 51st position, what term would be there, right? So in this case, it would be 3n minus 1. We'll get to this later, how we're going to actually find this explicit formula, but I could actually find the 51st term by plugging in 51 into this formula, and it should spit it out. Okay, so the next thing that we want to do is we want to look at some examples. Find the next 4 terms of the sequence. So first of all, I'm just looking for a pattern. Hey, what do you know? You can get to the terms by subtracting 4. So if I keep this pattern up, I should find the next 4 terms. Let's look at another example. Okay, I'm looking for a pattern. What's the pattern here? Well, I notice here that I'm subtracting, and I'm subtracting odd numbers that are the next biggest odd number. So if I keep this pattern up, right? If I keep this pattern up, I should find that the next 4 terms are -6, -17, -30, and -45. Each time I subtracted an odd number that was a little bit bigger than the last odd number. How about this one? In this one, we notice that they've actually given me an explicit formula. So what I'm going to want to do is I'm going to want to plug in 1 to get the first term, 2 to get the second term, 3 to get the next term, right? In other words, that's my explicit formula. If I keep plugging in different values of n, I should find the terms at each one of these positions. So this is A1. And this is A2. And here's A3. And here's A4. Right, all I'm doing is plugging in 1, 2, 3, and 4 into my formula to find the terms at each of those locations. So the first 4 terms in the sequence are 2, 9, 28, and 65. And all this is f of 1, f of 2, f of 3, and f of 4, right? Where I'm plugging in the position number into the function or the formula. All right, you try. Find the next 4 terms of the sequence. Remember, look for a pattern and then keep applying the pattern. You should have found that the pattern was divide by 3. Let's look at another example. Determine if the sequence is convergent or divergent. So again, we don't need a graph necessarily, but let's start by just finding the first 8 terms. So I've got 1, 2, 4, 8, 16. So where do you think this is going, right? Well, it looks like since these numbers are increasing, that the graph is going like this, right? The values that are positive are getting very, very big. The values that are negative are getting very, very large. Are all the values tending toward one specific value? No, they're going in opposite directions. So this graph is divergent. And therefore, my sequence is divergent. All right, how about this one? Determine if the sequence is convergent or divergent. So again, we're going to find the first 8 terms. And what do we notice? Looks like these values are getting closer and closer and closer to 0, which means the limit of this as x goes to infinity is 0. If I graph this, that's exactly what I see, right? I see that the limit as x approaches infinity appears to be 0, and therefore these terms or this sequence is convergent. All right, you try. Determine whether the sequence is convergent or divergent. So take a minute now to pause the video, find the first 8 terms, see if you can identify a limit, and then decide if it's convergent or divergent. You should have found that this graph is convergent, and therefore the sequence is convergent. All right, so we're going to look at series now. What is a series? A series is the sum of all the terms of a sequence. So like sequences, which can be finite or infinite, series can be finite or infinite. So I could add up like a handful of numbers, like for instance, this is just the first 5, right? So this is what we call a partial sum, or find the sum of the first 5. Or we could try to add all of them up. So this ... tells me that this is an infinite sequence. The sum of the first n terms is what we call the nth partial sum. In other words, don't sum everything, just sum the first n. Okay. So find the 5th partial sum. So again, they're giving me a formula. So I'm going to have to find A1, A2, A3, right? I'm going to have to find all those first, and then because it's a sum, I'm going to be adding them together. So let's first find the terms, A1, A2, A3, A4, and A5. And because this is a partial sum, I'm going to take all of those terms, add them together, and that should give me my partial sum of the first 5 terms. And I should get 40. All right, how about this one? Now this is a little bit different. This is the notation partial sum of the first 4 terms. Not any 4 terms, the first 4 terms. So I find the first 4 terms, A1, A2, A3, and A4. And after I found all of those terms, what do? I add them together, right? Because this is a sum. When you add all of those terms together, you get 45 over 8, or 5.625 as your answer. All right, let's take a look at this one. So now we're going to talk about how to use sigma notation to look at the sum of things. Sigma notation is just fancy shortcut for taking the sum of something. This guy right here is my explicit formula. That's the thing I'm going to be plugging stuff into. Then we have what's called the index of summation. The index of summation tells me what I'm going to be plugging into the formula. It's like a counter. So this on the bottom is the term that we start with. We keep plugging things in. So I would plug in k equals 1. And I would keep plugging in higher and higher values of k until I got to 5. That's the term that we end with. And the giant sigma is just the Greek letter. It's like a capital S, and it means take the sum. So for instance, this is my formula. I'm going to be plugging stuff into that. The first thing I'm going to plug in is 1. So notice I plugged in a 1. Then that 1 is going to get bigger. So now I'm going to plug in n equals 2. Now I'm going to plug in n equals 3. Now I'm going to plug in n equals 4. And then I'm going to stop because that's the end of the summation index. Stop at 4. And because I have a giant sigma, after I find the value of all of these things, I'm going to add them together. In other words, take the sum. So I get 0 plus 2 plus 6 plus 12, and I get 20. Okay, next example. Remember, I'm going to start by plugging n equals 2 in here, then n equals 3, then n equals 4, then n equals 5. Why do I stop at 5? That's where the end of my... Once I find the value of all of these terms, 1, 2, 3, 4 of them, then I take the sum of all of these, and I get 15.85 is my final answer. Okay, last one. I'm going to start by plugging in 1, right? Plug in 1, plug in 2, plug in 3, plug in 4, plug in 5. How much of these should I do? Well, it says to go all the way to infinity, which I'm not going to be able to do. So what I should do is add what I have and look for a pattern. What do you notice? Well, each term just adds 3 to an increased power of 10. So this is going to be 3 repeating forever, or 1/3. All right, you try. You're going to remember, this is your formula. You're going to start by plugging n equals 1. You'll keep doing that until you get to 5, and then you'll take the sum of all of those terms. Take a minute to pause the video, and then check your answer and see how you do. You should have found that the correct answer was C, 215.